Today we're starting in 5.6, direct and inverse variations. So the things that are going to be the very most important of this section are these formulas here under direct and indirect, which is also known as inverse variation. Now, direct variation has a main equation, y equals k times x. Now, when we compare that to what we were just doing in y equals mx plus b, the m value being our slope is what our k value is to our direct variation equation, okay? So a direct variation equation is a line with a b value, a y-intercept of 0, okay? So the direct variation equation is a line with a y-intercept of 0, which means that the line that you graph, being a direct variation equation, has to go through the origin, okay? Now, we're going to need also this formula right here, which helps us solve for whatever that k value is. And k is what we call the constant of variation, okay? And again, a direct inverse equation will have some slope k, but it will always go through the origin, okay? So we may have a line with a slope of what appears to be about 1. Then we may also have a line with a slope that appears to be about a 2, maybe another one with a slope of about 3. But the thing is, they all go through the origin. Okay, now an indirect variation or an inverse, terminology doesn't matter, they're both the same thing, gives us a y equals k divided by x. And when we solve for k, the constant of variation, we simply multiply x times y. And an inverse or indirect variation equation, when it's graphed, looks something like that, okay? So, obviously not linear. All right, so the goal here is to be able to not only write direct variation equations, but to look at a table of values and see if, in fact, the table represents either a direct, an indirect, or neither, okay? So that brings us to example 1. We're given these x and y coordinates here, okay? X, we have 1, 2, 3, 4, and then y, 7, 14, 21, 28. All right, so we need to find the k value. If this is a direct variation, y equals k times x, and k is equal to y over x. So let us first determine, using that first set of coordinates, what our k value is, okay? K is equal to y over x, which is 7 over 1. So the k value here is 7. In the next coordinate pair, y over x is 14 over 2, so the k value is 7. In this coordinate pair here, y is 21, x is 3, so 21 divided by 3 gives us that k, again, is 7. Likewise, 28 divided by 4 is 7. So what that tells us is that that table represents a direct variation because the k value that we solved for was the same all the way down the table. And that's very important that we go all the way down the table. We might get two values that are the same, and then we'll get to that third value and think, oh, that one's going to be the same too, and it's actually not. Okay? So, for example 2, It says find the constant of variation if y varies directly with x. When we look at that wording, it says y varies directly with x. That means that we are using the direct variation equation, which is y equals k over x. We are also told that y equals 6 when x equals 3. And it wants us to write the function rule for the variation. Okay? So if y is equal to 6 and x is equal to 3, what we get is that k is equal to 6 divided by 3, which gives us a k value, or again, a slope of 2. So we're going to go back and fill in our direct variation equation, putting the k value in place. And notice, because there is no number after the 2x as a plus or a minus, that means that the b value, the y-intercept, is actually a 0, which for direct variation, it has to be. Okay, so let's do another one. Let's find the constant of variation if y varies directly with x and y is equal to 12 when x is equal to 3. So we're going to find k and then write the equation, the function rule, okay? We're going to do the same thing as we did in example 2, okay? So first thing we're going to do is find k. And the formula for direct variation, y equals kx, means that k equals y divided by x, and k is equal to 12 over 3, which is 4. Now that we know what k is, we're going to put it back in to our direct variation equation, and there you go. So that is a straight line with a slope of 4 through the origin. Okay, now in example 3, it says if the distance traveled varies directly, there's that word directly, with time, Jose rode 12 miles in 45 minutes. How far can he ride in 2 hours? Okay, so here we're going to go back to our idea of ratios. Okay, and we're going to set up a ratio of miles over minutes. Okay, so if he can ride 12 miles in 45 minutes, how many miles can he ride in 2 hours? Now, 45 is in minutes, so we need to change 2 hours to minutes. If 1 hour is 60 minutes, 2 hours is 120. Now we will cross multiply and solve for x, okay? So we're going to multiply the 120 times 12, and then of course, once we do that, we're going to get x by dividing by 45. So that means if he rides for 2 hours, he will go 32 miles, okay? So in miles per minute, we can use that as a ratio. Solve for the number of miles as our unknown. In 2 hours, equivalent to minutes, which is 120. Okay? So once we know what that distance is, we could actually say that the constant of variation plugged in as a 32 would give us that as an equation. Okay? So, for example 4. We're looking now at inverse variations. Okay, so the values are inversely proportional, and we looked at what that meant as a graph. Okay, so in example 4, it says does the table represent direct variation, an indirect variation, or neither? Okay, so we've got all these x values. And likewise, y values. Now, if this is a direct variation, our k value will be the same every time we divide y by x. If this is an inverse variation, k will be the same every time we multiply y times x. So it's either one or the other, and if neither one of those rules apply, then it would be neither a direct nor an inverse. So let's start out by finding out if this is a direct. So we're going to divide y by x. So here, 72 divided by 2 gives us a k value of 36. Okay, so we're going to put the k's in this column here. And then 36 divided by 4 gives us right off the bat a different k value. That tells us that this is not direct variation. So let's change it up, and we'll see if it is in fact an indirect variation. So y times x will give us a k value. So 72 times 2 gives us 144. 4 times 36 gives us 144. 8 times 18 gives us 144. We know 12 times 12. 16 times 9, 24 times 6, and 48 times 3. All of those are 144. That means that this is an example of an indirect variation. Okay? And now that we know what k is, we can go back and fill it into the indirect variation equation to get y is equal to 144 over x. Okay? So another thing that we're going to be doing is looking at the ways in which we can use direct and indirect variations with substitute equations. Okay? What we just saw in the example 3 was that in the indirect, we were able to use a ratio, okay? So it was D1 over T1 is equal to D2 over T2, okay? In other words, we could say y over x is equal to y over x, okay? And of course, these y's are different, as is these x's are different from each other, that is. So we could say y1, x1, y2, x2, okay? So an indirect also has an equation, okay? Which would be x1, y1 equals x2, y2. All right, so let us get rid of this one. Okay, and we can move this one up, and we'll do another example out of all of these. And why did that not stay there? Okay, well, that's all right. Let's just rewrite it. Let's say y1 over x1 equals y2 over x2. Or you could have x1 over y1 and x2 over y2. Either way, it doesn't matter, okay? As long as if you keep y's on top and x's on the bottom, you're good. Okay, so we're looking at example 5 in an indirect variation problem. that involves this equation here. The number of census workers varies inversely. That's how we know we're using indirect, the word inversely, okay? It varies inversely with the number of days it takes to complete the census. If it takes 24 workers 15 days, how many workers will it take to do the census in 10 days? So 24 workers in 15 days, we're looking at how many days, or how many workers, are needed to complete the job in 10 days. Okay? And the reason that we set it up like this is because we were told it was an inverse. Okay? So 24 times 15. And then, of course, all divided by 10 would give us 36. Now, if we were looking at that same type of a problem, but it read the number of census workers varies directly, okay, we would use the same information. 24 workers in 15 days. How many workers in 10 days? Okay, that would give us a totally different equation, okay? Totally different equation. And we would get 16 workers, okay? So depending upon whether we're told it's direct or inverse, we'll also determine then what version of the equation we have to use. Okay, and one more example. This is Hooke's Law. And for those of you that are going to be taking physics with me in a couple of years, will have the benefit of learning about Hooke's Law in springs. Okay, Hooke's Law states that the length of the stretch in a spring is directly proportional. Now, directly tells us that this is the version of the equation that we are going to be using. Because of the word directly, we're using direct variation, okay? If a spring stretches 8 inches when a weight of 20 pounds is put on it, how far will it stretch when a 50-pound weight is put on it? So remember, it's going to be y1 over x1 equals y2 over x2. So let's say we'll do inches and pounds, okay? It stretches 8 inches for 20 pounds. How far will it stretch when 50 pounds is put on it? So 20x equals 400, and then x will equal 20. In other words, it will stretch 20 inches with 50 pounds because it stretches 8 inches with 20 pounds. Okay, so that is inches. And we set up our ratio with inches on top and pounds on bottom. Okay, very, very basic. Okay, good job, guys.